Hello and welcome to the Allplane Podcast, here with the people that are redefining the future of commercial aviation. And as usual, before I introduce today's guest, let me remind you that you can find all the previous episodes of this podcast, as well as many other aviation stories on the Allplane website. That's Allplane.tv, Allplane.tv. Today we are going to touch upon a topic that is essential to any discussion about aircraft electrification, and that is the state of battery science and what can we realistically expect in this field in the coming years. Our guest today is Venkat Viswanathan, one of the leading experts when it comes to batteries for the aviation industry. Venkat is an associate professor at Carnegie Mellon University in Pittsburgh, Pennsylvania, where he leads an interdisciplinary research group working on technologies with the potential to accelerate the transition to sustainable transportation and aviation. Venkat holds a PhD from Stanford University and is also an advisor at several companies in this space, such as QuantumScape and Ionics, and previously he had also been a technical advisor at Zunum Aerospace. He's also the co-founder of Cement, a startup that helps decarbonize industrial processes in the cement industry. In the last couple of months, Venkat has co-authored a couple of papers that have been published in major journals, Nature and Proceedings of the National Academy of Sciences, in which he outlines the results of his work in the field of batteries for aircraft and the several possible courses of action that are open to the industry. But above all, Venkat is a great communicator and he has a great ability to break down complex scientific concepts and explain battery chemistry to a wider non-scientific audience. So, without further ado, let's welcome Venkat to the podcast to get the latest expert insights about batteries for aviation. Hello, Venkat. How are you?
Good. How are you, Mia?
Very well. Where are you joining us from today?
I'm joining from Pittsburgh, Pennsylvania.
Very cool. So first of all, let me introduce you to the audience. You are an associate professor at Carnegie Mellon University in Pittsburgh, Pennsylvania, and your area of specialty is battery science. You've been working very intensively in solving one of the major issues of aviation electrification, which is actually how can we get better batteries? How can we get batteries that provide more energy density so that we can electrify aviation further? So we're going to cover this ground now, but first of all, I will ask you to provide us a bit more of a background about your professional and academic background, and then we can maybe move on to talk about a couple of very interesting papers that you published recently in two very prestigious journals about science of batteries and how this science of batteries can evolve and what we need to do in the near future to move forward in this direction.
Definitely. So I think the journey to electrification is actually one largely by accident, right? So I was a graduate student at Stanford University, and I was seeing the transition to electrification of transportation. So that was when I started actually thinking about batteries, largely by accident. And I think I have spent now since then, probably over 15 years in this field. And I was razor focused on trying to understand batteries for electric vehicles. And in this context, I think one pivotal point in my mental thinking was a road trip I did in the summer of 2017 from Pittsburgh to Palo Alto with my wife. And we drove in my 60 kilowatt hour electric vehicle. So it had about 200-ish mile range. And of course, I wouldn't say it was a cakewalk, but certainly it was not as difficult as I had originally imagined to be able to do a cross-country trip in an electric vehicle. And in that trip, I realized that I'm inventing all these advanced batteries, and where are they going to go, right? If not for next generation of electric vehicles. Then two interesting things happened that summer. One was I got invited to attend a workshop that NASA organized that brought together battery people and aviation people. It was the first time I met a number of folks that subsequently have played a great role in my understanding of aviation. One in particular, Brian German, who had just then co-authored the Uber Elevate white paper, setting the stage for urban air mobility. And then folks that had thought about aviation electrification for larger aircrafts. So on the road trip back, I spoke on the phone with Ashish Kumar, then co-founder and CEO of Zunumero. And that was sort of that summer was the pivotal moment in my career where it was clear that I had to sort of transition to aviation, as that was a frontier where I could make better batteries, which will have sort of infinite need because whatever high specific energy battery I could invent, there was a market to address. And so I think that's sort of the large context. And then a number of sort of key things happened subsequently. Once I sort of said I'm going to work on this, one significant thing was I was then signed on as a consultant at Pratt & Whitney, and I reported to Alan Epstein, who then became a co-author in one of these papers that we're going to talk about today. And it was a great period where over a period of about 12 months, I taught him all about advanced batteries, and he taught me all about aviation. So it was a good deal for both of us. And then in the summer of 2018, the Airbus Vahana team came to us and then asked us to think about batteries for eVTOL. And that really, I think, started the journey for us in the eVTOL space. And then I think a number of people there, two people that were our project managers, Jeff Bauer, who then went on to be chief engineer at Archer, and then Evan Frank, who leads propulsion at TD Hawk, and now. And with that, we got our hands dirty in the aviation space. And so I think that culminated our understanding, and I think that led to these two papers over the last 3 months or so, which I think has really put both the battery industry and the aviation industry on alert in terms of sort of what are the capabilities that might be possible, right? I think that's the sort of key goal of this work, is to understand where we are today, but also to project where we might be from the lens of someone that really understands the electrochemistry of what might be possible. I think in aviation, I think it is common trade studies to be able to project what happens in the future, and those typically run at sort of single-digit percent, right? Couple percent, 3% per year. But the advantage in batteries is we're just starting, right? I think we're just starting in this era of battery-powered mobility, battery-powered propulsion. So there is a long way to go. And I would say that, it's, in many ways, in terms of battery electrification, it's like, back to the Wright brothers era, right? So we're just at the beginning.
Yeah, actually, one of the examples with which you illustrate your paper on the Nature journal is actually from the 19th century, end of the 19th century, one of the first airships powered by an electric battery-powered engine, which is a detail I was not aware of. Really, really interesting. And then, yeah, as you mentioned, at the end of last year, you published these two papers. I'm going to post the links, of course, in the show notes, but just let me mention them. One, it's on Nature. It's one of the most prestigious science journals, and the title is "The Challenges and Opportunities of Battery-Powered Flight." It was published on the 6th of it was published on the 26th of January 2022, although it was accepted it was received in November, October. Sorry, I just mistook the dates, but yeah, basically it got published at the end of January. And then earlier on that one is in November, you published another paper on the proceedings of the National Academy of Sciences of the United States of America, and the title is "The Promise of Energy-Efficient Battery-Powered Urban Aircraft." I'm going to post links to both papers, but I'm going to ask you to go over the main findings. Basically, one of the things you say, I'm not a scientist, so I'm not going to get too much into the details, but you say that one of the things that we need for battery power electric aviation to go forward is actually we need a radical change in the sort of approach, because the technologies that have been powering the batteries that have been powering electric vehicles on the ground, electric cars, are not sufficient for the demands of electric aviation, which is something that we could somehow suspect. We are aware of their limitations. Just to put some numbers, a Tesla Model 3 has an energy density. The battery has an energy density of 260 watt-hour per kilogram, yeah? And you said that with new approaches to battery technology, it's possible to get by 2030 to get to 600, but eventually we would need to get much farther than that, over 1,000 to 2,000 watt-hour per kilogram So, yeah, can you tell us basically what's the essence of these papers and what were your findings and what do you think, what are the limitations with the current technology and what do you think are the most promising paths to move on to the next stage?
Yeah, definitely. So I think maybe before I sort of jump into the details, I'll just set sort of the context of how we got to this so that the listeners get a sense for the lens at which we have approached this problem. So I co-authored this paper with 6 other co-authors, and four of them came from aviation, and then 3 battery people. And it was really trying to and of course, as I mentioned earlier, right, Alan Epstein led the aerospace section, and then I led all the sort of battery discussion. And the core approach to thinking about this problem was to take a uniquely sort of aerospace-like thinking, which is an entire system-based approach to ask the question of what might be feasible, and also what are the sort of unique challenges that aerospace has that is different from automotive. So I think the sort of larger message that you already got to was that the arc of progress in automotive batteries is not going to meet the aviation requirements. I think that's a point that many of your previous guests have made, and I think one that I think is quite clear. The question is.
Sorry, may I interrupt you here 1 second? So this 260 watt hour per kilogram now that we have with Tesla now, how long did it take us to get to this point?
Yeah, so that's a great question. So the original start of the earliest invention of the lithium-ion battery, which happened in 1991, the cells there were about 150 watt hours per kilogram, and then from there it's taken us almost close to 2.5 decades to be able to get to where we are today with cells in the range of 260 to approaching 300 watt hours per kilogram. I will add one important caveat, which is that the relevant number to use when you want to integrate that into a device such as an automobile or an aircraft is the packaging. So it's the pack level specific energy. So the cell has reached 260 to 300. But the pack is still in the range of about 180 to about 200 watt hours per kilogram. So that 600 number that you mentioned is what we think the pack will get to. We think cells will get to about 800 to 1,000. So there's what's called a packing burden from an amazing cell to what you can use for a variety of reasons, extra packaging that you need to be able to use in a aviation propulsion system.
Sorry, can you please clarify very briefly for the audience it might not be familiar with the concept of cell and pack? What do they mean in plain terms?
Yeah, let me unpack that. So the cell level specific energy is basically a cell that you might be able to buy. For example, right? So people have probably seen cylindrical cells, the lithium-ion cylindrical cells that they may buy. The cell level specific energy is the energy contained inside that cell divided by the weight of that cell. So you put that in a weighing machine, and then you get the weight, and then you get the energy content of the cell, and the energy divided by the weight is the cell level specific energy. Now, in any relevant propulsion system that you would use these batteries, you would have many thousands of these cells. These cells need to be connected, right? So they need to be connected electrically. They also need to be shielded from each other. So you need to package them between each other so that if one cell fails, the failure doesn't propagate to other cells. And then the final thing is, even though it has 100% of the energy, you don't use 100% of the energy, right? You use only maybe 90% of the energy, which is you charge from 5% all the way, discharge all the way to 5%, and then charge all the way to 95%. So you lose another 10% of the battery. So pack level specific energy is the automotive battery pack or the aviation battery pack, the energy contained inside that full pack divided by the weight of the pack, right? So as you might expect, right, that is lower than what you would get from the cell because you now have to add the weight of additional components that are not providing you energy, right? So the packaging, the electrical wires, obviously the window that you are limiting it to, and so on. So for listeners, in figure 3 of that paper, we unpack all of these different factors. And the important point we make, which is I think very interesting, is that you get a fresh cell, right? You only can use 45% of that fresh cell's energy in terms of what you could use for flight, right? And in fact, even there, you eventually end up having to put some for reserve, right? So which means that you end up having a much lower fraction of the total available energy inside the cell for actual flight, right? And I think this is something that I think is not fully appreciated.
When you mention a fresh cell, you mean a cell that hasn't undergone any, let's say, depletion on the capabilities, I guess.
Exactly.
So that the typical thing that you have a computer or you have a telephone, and over time, the battery is not as performing that when you bought it the first time, right? Because there's a depletion there.
Yeah, so that's an additional aspect. It's in addition to sort of the stuff that we talked about, right? Which is that as the battery ages, then the performance of the battery, both in terms of its ability to deliver energy, as well as the ability to deliver power, decreases. And so I think that's another factor that you need to take into account in order to decide what the available energy and available power is.
Okay. Sorry, I interrupted you earlier. Just to get an idea of the pace at which this battery science has been advancing over the last 2 decades. So what are the perspectives now? I mean, you say that a new paradigm is needed to move faster. So is this due to the materials? Is this due to the way that the batteries are produced? Is this due to new revolutionary approaches to technology? Tell us a bit more about how you see this thing evolving.
Yeah, so I think the pace of progress is a great way to think about it, right? So if you sort of took a macro view, right, we're progressing at about sort of 4 to 5% a year over the last 20, 25 years. But if you actually look at the micro trend, which is if you look at the progress over the last 5 years, it's pretty incredible. If you look at what has happened with one particular technology, lithium metal, where what you do is you change the anode that's used today's batteries, which is usually graphite, and then maybe a little bit of silicon. You remove the graphite, and then you directly use lithium in its metallic form as the anode. And it turns out that if you do that, you can now reach specific energies in the range of 400 to 500 watt hour per kilogram. This is not a new idea. This has actually been around from the 1970s. We just didn't have the tools to be able to control this, right? So this was one of the hardest problems in battery science. We call it the holy grail in battery science. And over the last 5 to 6 years, there's been incredible effort in making that happen. And today we have credible demonstrations. And in fact, you had one of those great entrepreneurs, Richard Wang, on your show.
From Coburg, which is now a part of Northvolt, which is one of the largest battery makers in Europe, well, in the world actually. And they just opened this new gigafactory in the north of Sweden. They acquired Coburg, which is an American startup working precisely on this lithium-metal technology, and Coburg is going to be, let's say, the sort of like the test bank for aviation-oriented technologies of Northvolt. Yeah, that's batteries for other applications as well. Yeah, it's good you mentioned it. Lithium-ion gets most of the press, but there are other technologies out there undergoing development.
Exactly, and so and of course, I have been part of lithium metal in other capacity, and I've been involved with QuantumScape, which is also commercializing this for automotive applications. And so you ask the question, okay, so we've solved the problem, the holy grail on the anode side. Can we solve the holy grail on the cathode side, right? So you can either change the anode or change the cathode. And I think with lithium metal, the end is done, right? So you are not going to do anything better than lithium metal on the anode side. So the next is to do something on the cathode side. And so figure 5 in that paper sets the context for this. And so the easiest way you can think about it, you probably heard these kinds of terms, NMC, NCA, LFP, all kinds of terms to describe batteries. And really the core thing that you want to take away is every one of those things will have an element of metal, a transition metal. NMC has nickel, manganese, cobalt. NCA has nickel, cobalt, aluminum. LFP has lithium iron phosphate, so iron. The key is for every one of those technologies, for every metal that you have, every single metal you have, you can store 1 lithium. If you have 1 iron, you can store 1 lithium. If you have 1 nickel, you can store 1 lithium. And this has been the cornerstone of innovation in batteries, which goes by the term insertion or intercalation, right? That's the core idea. Now, the paradigm that we put forward in the paper is to move beyond that 1-to-1 ratio and store more than 1 lithium per active center, whatever it is, right? And ideally, that active center is not a metal. The problem with metals is they come, if you remember your high school chemistry, right? They come in the lower part of the periodic table. The second things go into the lower part of the periodic table. They're heavy, right? So
yeah, it's very rusty, my high school chemistry.
in fact, the rust itself, right, is the core element of modern lithium-ion battery, because it's the rust, the iron, iron ore that we end up refined to make lithium iron phosphate. So the core idea is, how do we store more than one lithium per active center? That's the core question that we went after. And we put out a number of possible options. And this goes by the larger family called conversion instead of insertion. And in the conversion family of electrodes, the one shot on goal that we clearly spell out is what's called CFX, carbon, fluorine, and X here is the amount of fluorine you have. And so the beauty here is that you can now store, you now have done away with all of the transition metals. So there's no metal. So it's very light elements, carbon and fluorine. And you can now potentially store a lot of lithium in the system. And in fact, you might ask the question, well, why is there any hope that this could get there? You can actually go out and buy a lithium CFX cell, so one that has a lithium metal anode, right, that we have talked about, and then CFX, that is 800 watt hours per kilogram today. So you can actually go and do this, except it can only be used once, right? It's a primary battery. It's not a rechargeable battery that can be used for any mobility application, right? So this is like the single-use rocket was the reusable rocket, right? Obviously, the cost of the single-use battery would be very high, but I think there's good reason to believe that we can make it rechargeable and we can make it achieve all of the other requirements that are needed for aviation.
But are these batteries, these technologies, you say they are available, but are they available commercially? So
yeah, they're available commercially.
So there are companies doing them, and for which type of applications? Is there a market for this?
So there's always a market for high energy density single-use batteries for military, defense, and other niche applications. So there are actually a number of companies that specialize in this lithium CFX battery. Eagle Picture is one of them, for example, and they have been working on this technology for many years. So you can actually buy these batteries commercially. They're also sometimes used for space applications as well, right? So where the other metrics are not so critical, such as rechargeability, right? You're okay with using it once and you're happy with it. So there's a number of sort of applications in that realm that have use for these kind of batteries.
Mm-hmm. And in environmental terms, is there any counterindication? I mean, all these chemicals, do they have any secondary effects on the environment or any other things that we don't want?
Yeah, I think the modern lithium-ion revolution, right, has caused a strain on the metal supply chain, right? So certainly with nickel and cobalt, the demand on nickel and cobalt has led to supply chain constraints. And of course, the other thing to remember is that typically when you make a kilowatt hour of a battery, you use up much more than a kilowatt hour of energy to be able to make that battery. So which means that you have to use them substantially over the lifetime of the battery to be able to recover back the energy cost associated with that. I think with CFX in particular, I think some of the challenges will be on figuring out efficient ways to make the electrode. So making fluorinated materials is tricky and will require some technological innovation. But I think none of these are showstoppers. None of these are things that are insurmountable. We know the challenges that lie ahead, and I think there's a lot of interesting innovation on fluorination that has come in the pharma space, where people that are making interesting drug-like molecules want to make those same kinds of compounds, and so they have invented some interesting techniques. So there's, I think, an exciting cross-pollination of ideas between these two communities that might be useful. But I think in the long term, I don't think there's any significant environmental roadblock to be able to make these materials and then build batteries out of them.
So you see this as a sort of a step-by-step ladder where now we have this lithium-ion, would then maybe lithium-metal be the next step, and then the step after that would be this fluorination technology that you mentioned?
Yeah.
So they would be it would be like an evolutionary ladder, or they could be maybe coexisting for different types of applications. How do you see this going?
Yeah, so I think it'll be a coexistence, because I think the beauty about aviation is that there is a spectrum of needs. I think much like automotive, but I think aviation even more so. I think with urban air mobility, and I think we'll get to some of that in the other paper. But urban air mobility, I think current lithium-ion has an important role to play. Current automotive grade lithium-ion. Then, of course, with longer range urban air mobility as well as regional air mobility, I think lithium metal will play an extraordinarily important role in that segment. And then for aircrafts beyond that, where you want to fly lots of passengers, lots of distance, we will unlock newer and newer markets with higher energy density cells, like the fluorinated electrodes that we just talked about.
When you say lots of passengers over long distances, can you put some figure or realistic figure on that? Because obviously it's not the same to fly, I don't know, 100 passengers on a relatively short flight. With still a step up from the eVTOL or from the sort of very light aircraft we are seeing now. But flying like intercontinental, that's a completely different game. What sort of applications you have in mind here when you say that that this technology is gonna bring a lot more range, a lot more capacity?
Yeah, so I think one interesting way in which we close the paper, right, as you pointed out at the beginning, right, we start the paper with the La France, right, which was the battery-powered dirigible that flew
their ship
8 kilometers with
in 1884. That was
1884, right? And in fact, I also realized this as I was writing this paper. My co-author, Alan Epstein, brought this up. And of course, in 1909, right, when the Wright brothers delivered the first airplane to the US government, right, which was capable of carrying 2 people, 120 kilometers, right?
Sorry, 1909. So that's about 6 years after what's considered to be the very first power flight. Yeah.
And I think that's about the capability of the Pipistrel aircraft, right? Another guest of yours.
Indeed.
So, and then if you remember in the arc of history, right, in 1920, there were fueled aircrafts that were carrying tens of passengers, about 800 kilometers or so, right? I think with the kind of batteries that we're talking about here, I think we'll start to be able to do the 1920 mission again, within this period. And then I think beyond that, will require a combination of innovations, right? So it can't be just from chemistry innovations. It has to be the integration of some chemistry innovations with other innovations on battery packaging, right? And we can get to some of those things. And I think those paired together will slowly start to move to larger and larger numbers, right? And I think the numbers that we put out in that paper, and I think figure 2 shows the gap between the usable energy density inside a turboprop and a turbofan versus batteries, right? And it's on a logarithmic scale, so which means that any gap, right, is very, very large, right? And so the numbers that we need are beyond sort of the numbers that we have even identified options for with near term. I mean, I think we've identified certainly options that eventually could get us to commuter aircraft, and of course larger aircraft to fly larger range missions, right? It's in the order of 1800 to 2500 watt hours per kilogram. So another factor of 2 from the kind of numbers, factor of 2 or 3 from the kind of numbers that we are talking about here. But I think you'll slowly unlock these things because just like what happened in electric vehicles, once you went electric, other things started to change, right? For example, right, when you went electric, once you could redesign the vehicle, then car designers figured out other ways to make the cars more aerodynamic, right? For example, the Model S and the Model 3 have the lowest drag coefficient of vehicles in that category, including all internal combustion engine vehicles that were known, right? So I think once that happens, once the unlock happens with electric propulsion, I think there are lots of other synergies that needs to be exploited. And I think in the urban air mobility space, right, this is very clear with distributed electric propulsion, where instead of one or two large fans right now, or one right now, you have many distributed either rotors or fans that allow you sort of much greater efficiency. And so I think if we think about what might be feasible with just the chemistry, I think I'm fairly confident that we will be capable of flying that 1920 mission again very soon.
Mm-hmm. But let's say, for example, the aircraft types that are now carry the bulk of passengers, like the Boeing 737s, A320s, do you think this size of aircraft will be electrified in a, let's say, in a reasonable time frame?
I think it will require the third generation of this innovation, right? In the arc that we just talked about, lithium metal, and then fluorinated electrodes, and the third generation will start to unlock the 737, the A320s. I think I think we need to sort of go in steps, because there's substantial hurdles to be able to manage safely that scale of energy and be able to bring down the weight enough such that you can address the needs of those kinds of aircraft.
You touch on the safety issue. What about the safety of all these different technologies that are not lithium-ion, like lithium-metal and fluorination? What's a safety profile, and what sort of precautions are going to be needed?
Yeah, so I think aircrafts and the entire aerospace industry is built on the foundation of safety, as we point out in our paper. And lithium metal, certainly, the reason it was abandoned in the 1970s and 80s actually was safety, right? So because what happens when you charge and recharge the battery is they form these so-called dendrites, the same kinds of beautiful snow dendrites that form that you see in winter. The very same thing happens inside the battery. It actually forms for the exact same reason that you form snow dendrites. But inside a battery, it's a problem because once that dendrite grows from one side to another side, then there is an electrical connection inside the battery from one electrode to another electrode. That causes a short circuit because you only want the electrons to go through the outside, not through the inside. So the short then leads to a thermal event, and that leads to, of course, fire, as popularly called, right? So that was one of the reasons why lithium metal was abandoned in the 70s and 80s. And that's exactly the challenge that has been addressed now to be able to make them at the same safety level as lithium ion.
This has been fixed.
This main issue has been fixed, right? So the expectation is that the safety profile of lithium metal cells would be comparable to lithium ion cells. So we'll have the same kind of safety profile that we have with lithium ion cells. Now, even in lithium-ion cells, the safety profile is not as good as it could be if we could do just one thing, which is to replace the flammable electrolyte, right? So the electrolyte that's there is like fuel, right? It's an organic compound, right? Much like jet fuel, kerosene, or gasoline. And if we can find ways to replace that or modify that, we can bring up the safety profile of current lithium-ion batteries as well, right? And there's a lot of work going on, a lot of innovation going on there. So lithium metal, the expectation is that it will have similar safety profiles. With these fluorinated electrodes, I think it remains to be seen because I don't think we know enough to be able to comment on the safety profile of this. But I think certainly if you have to get anything that has to meet aviation needs, it has to be safe.
Mm-hmm. You also mentioned other advances like robotic experimentation or machine learning driven new material science advances. Can you elaborate a bit more on this? And what's characterization? Because that's another term that appears in the paper. I'm not sure I fully understood.
Yeah, absolutely. Let me unpack those three for you.
Sure.
So maybe let's do the characterization first. So in order for us to be able to make these batteries rechargeable and reversible, the lithium atoms have to move from one side to another side and up and down, back and forth every single day. Right? That's what happens when you connect this to a power outlet or when you use it. And so in order for us to be able to control what happens, we need to be able to watch what happens. Like we need to be able to really understand what is happening inside microscopically. And so what I mean by characterization is just like how we go and take a photo outside and be able to watch what happens, or for example, we go to a wind tunnel and make measurements, right? In the same way here, we want to be able to take measurements and watch what happens, right? Just like you would with a PIV for the velocity field or pressure field in an aviation context. We now want to be able to understand and watch what happens inside the battery. Right? And that's what's characterization. And so the two terms we use in our paper, in situ and in operando. Right? In operando is, while the battery is operating, we want to observe what happens, right? And I think the capabilities that have been enabled in situ and in operando have enabled us to design better batteries faster than ever before, right? So if you know and if you can watch what's happening, it's easier to fix the problem, right? So the capabilities that are there today versus even like 5 years ago is incredible, right? I mean, there's been step change in characterization capability. The second one that you talked about.
So we have the first major trend that can help support this push forward in batteries characterization. Second one, we have the robotic testing, I think.
Yeah, exactly. And maybe I'll quickly just talk about the robotic experimentation. We've built two robots, Otto and Clio, that without any human intervention can go look for an electrolyte, mix, test them, decide what to do next, right? And all of this without any human intervention. And I think what this allows us to do is search over the chemical space and bring down the amount of heuristics, right? Bring down the amount of trial and error, which has been the way in which the battery field has been moving.
But how does it happen in practice? I mean, there's like a lab where you have a robot mixing chemicals or something like that?
Exactly. So it's a microfluidic setup. You have a bunch of different electrolyte compounds. You then mix them, send it to a test chamber. So through a microfluidic setup, you send it and then test in an electrochemical device. So test in a battery that is sort of mimicking the true battery. And then you get the answer. The answer is processed live. And then using that answer, there's a machine learning sort of model that decides what's the next compound to mix and test.
Okay, so it's processing kind of feedback on the go, depending on the results he's getting. And I guess that makes it faster and more precise.
That makes it faster, it's more precise. And the beauty is you can adjust on the go. If you look at human experimentation, the way we would do it is we say, okay, I'm going to do these experiments today, right? And then I only focus on doing the experiment. I don't focus on analyzing the answer as the results are coming and deciding what to do next, right? So usually I just do what I planned for the day, right? And that could be that I basically, in the second experiment, I knew that everything I'm doing today is actually not useful, but I'm not thinking, right? Because I'm actually just focused on doing. So the beauty with the robotic setup is then it takes the headache away from us for doing the experiment so that we can analyze and then say, okay, this tells us that this is not the right direction to go. Instead, it's this direction. And so that allows us to move to another direction.
And that takes us to the third leg, is the machine learning research, machine learning based research on new materials.
Yeah. And here, actually, I'm involved with a company called Aonics, where I'm chief scientist, which is commercializing these solutions to companies. And the core goal of both Aonics and this sort of vision is to be able to shrink the time taken to commercialize innovation, right? And if you ask Richard from Kuberg or others that have commercialized these battery innovations, right? The number of experiments they have done to get to their secret sauce or the secret recipe is of the order of somewhere between 100,000 experiments to about millions of experiments.
Wow.
Right? That's a lot of experiments, right? So we clearly have to bring that down, right? And so the vision with machine learning is before you even test, you already have a very good answer of whether it's going to be good or not. And with that, you can basically shrink that both number of experiments and time down, right? The other thing is the amount of money invested, right? So they all have invested of the order of hundreds of millions of dollars to be able to get to that secret recipe, right?
But sorry, is this because this is done? Is this because it's processing the data from real life physical experiments, or because it's modeling and it's just doing it virtually, doing, let's say, like theoretical experiments?
It's both, right? So it's the combination that allows this to work. It's running both modeling, theoretical sort of experiments, as you described it, and real experiments. So it's extracting maximum value out of the real experiments, and then combining that with what we can do with theoretical experiments. And of course, the new innovations in machine learning that allows to build a map between the identity of the substance to its performance, right? So before, we didn't have this kind of a fidelity in terms of mapping the identity of the material. For example, the identity of the kind of separator being used to its function in a solid state battery, right? So what you had to do was to take that material, make the material, build a cell, test, and so on. But now we are at the point where we can go from the identity to the performance quite easily. And of course, pairing all of that together, it's the package that I think is enabling rapid innovation in this machine learning guided discovery. It is both using simulation and theoretical experiments in combination with real experiments, right? I think it's very, very key that real experiments are a part of this loop, because otherwise the theoretical experiments have its deficiency in how well it can simulate the reality. And so it cannot live by itself. It has to be used in conjunction with the real experiments that allows us to sort of optimize over these design spaces.
Mm-hmm. Yeah, well, I guess it helps you narrow down a lot the real life experiments. And I guess that's also why you are confident that we're going to come up soon with all these new materials for batteries.
I've seen it happen. I've seen it happen personally, right? So I think the pace of progress and the pace of innovation in the battery industry is going to be unprecedented in the coming decade. The other axis that I think is not mentioned is the excitement students feel to work on batteries, right? Mm-hmm. So when I started as a professor, the excitement for batteries, right, I would have to sort of go and say, no, batteries is a really important problem. Now it's the opposite, right? Students are coming and saying, can you teach us more battery classes, right? So my battery class is always oversubscribed, right? And so the excitement in young, innovative people on working on these important problems, I think that is, you cannot substitute that. And I think that's why, in addition to all of the other three trends that we talked about, right, just the passion for sustainability that is there today, I think that is a key factor that will allow us to innovate much faster.
Mm-hmm. I see. So batteries are hot. Well, they shouldn't be hot when they are on a plane, right? But they are hot in the academic world. Yeah. Okay, so that when it comes to the chemistry, but then you also work on the field of advanced air mobility and urban air mobility. You said that you are more, let's say, more optimistic about the prospects of the current lithium-ion technology for urban air mobility. Did I get it right?
Yeah, so I think in that Proceedings of the National Academy of Sciences article, we set out to answer two questions. The first question was whether today's batteries or near-term batteries can supply the needs of urban air mobility, right? So I think that was the first question. And the second question, which I think is an important question that every student that works in this topic asks me, is, are these just sort of replacing, are these the sort of gas guzzling version in the air, right? So are these the sort of, the Hummers in the air, so to speak, right? How energy efficient are they, right? So the paper really addressed those two questions. And so what we analyzed there was we took a number of aircraft designs, some lift plus cruise design, tilt rotor design, tilt duct design, and then we asked the question of whether today's lithium-ion cells can supply two main things. Can it supply the specific energy, so how much energy it has per weight, as well as specific power, right? And the specific power is the really important factor that is unique to UAM and AAM, that makes it different from automotive applications, right? You never...
Sorry, just parenthesis here. Can you elaborate a bit more about the difference between energy and power? Because I'm assuming this is a distinction that it's for many people is not so clear.
Right. Yeah. So how much energy is there? So if you look at sort of your phone, right, or your car, how much energy is there is what's shown in the indicator, right? I have 80%, right? So that says that I have 80% of the full energy that was there in the cell that is available. Power is how quickly can you use that energy, right? And so, for example, if you look at a car, right, they give you a spec for how fast you can accelerate, right? So that's an indicator of power, right? So how quickly you can get the energy is power, and the actual energy contained is your indicator.
Can we say in plain terms, is the difference between having, like, let's say, the stock and the flow?
Yeah,
how things are stored and how things are used to do? Yeah. Okay.
Yeah, exactly. So if you have a tank, so in that same analogy, if you have a tank, right, how heavy, how much liquid is there in the tank tells you the energy. how quickly you take water out of the tank tells you how much power. And so for urban air mobility, the second one, how quickly you can get that water out of the tank, actually is as important as how much water you have in the tank to begin with.
Is it because of the demands of the hovering and the vertical takeoff that many of these devices rely on?
Exactly. So it actually is on exactly that. But it turns out that the main challenge is actually the landing segment, not the takeoff segment.
Really?
Because so you actually end up requiring almost the same power when you land, because you have to sort of push the air to be able to land. And the problem, and this I'm sure all of your listeners would have felt when they are trying to use their smartphone, when suddenly your battery is at 10% and you try to play that YouTube video, right? It suddenly starts to freeze and turn off, right? The challenge is you need to deliver that high power at low state of charge. So when your battery pack has now gotten to, let's say, 30% in an eVTOL, and so actually the landing power is the failure mode currently for batteries that are used in eVTOL applications.
Mm-hmm. So basically, when there's less energy in the battery, let's say it's more challenging to have this peak power application.
Exactly. So the reason for that is actually quite intuitive. So I'll try and give you a simple way to think about it. So as you discharge the battery, right? So in the same way that you discharge water from a tank, right? When you open and try to get water from that, right? You now have a lower pressure head to be able to push this out. So in the same analogy, in that same water analogy, right? In a battery, there's less voltage to push, and so as a result, you're not capable of delivering the same power.
Okay, understood. So getting back again to the lithium-ion capabilities, what can be achieved with the current technology, or do we really do all these projects to have like urban air mobility in the near future? Because some of them are aiming for 2025 to 2026 launch dates. Do we need some significant advances in lithium-ion technology to happen in this very short period of time, or with the current technology we are already on good track to achieve that?
So I think the punchline of that paper, I think much to our own sort of surprise, was that I think a number of these designs are within the reach of current or very near-term lithium-ion technology, right? So I think that was the key insight from that particular work, and that shows that both the maturity of the industry, as you pointed out, in terms of how they have planned their certification approaches in the mid-decade, as well as the cells that will be available to them by that point, right? So by 2025, I think just the arc of lithium-ion will be able to get to high cycle life and get to the safety profile and get to the charging speeds needed for urban air mobility. And so I think the closing remark there in that paper was that this technology, and of course flying cars, right, is the epitome of technological progress, right? That it may be here sooner than most people think, because of the fact that there's exceptional progress and interest in urban air mobility, as well as the rapid progress in lithium-ion batteries that has already gotten it to a point where these designs are approaching feasibility already today, right? And think will only get more and more feasible in the coming years. So I think by the mid-decade, a number of these urban air mobility makers have announced plans to certify and run operations. And I'm very optimistic that, at least on the battery side, right, one that I know very well, we will have the batteries ready for them to be able to fly. It's the question of whether all of the other pieces, maybe autonomy and certification and regulation, other challenges, noise profile, lots of other aspects that needs to be addressed for this to be real. But I think from an energy source standpoint, urban air mobility is within striking distance. And I think what we learned there will teach us what to do in the other step changes that we talked about earlier.
To be clear, though, when we talk about urban air mobility, we are talking about really local movements. Like, I think you mentioned somewhere in your paper something like less than 10-minute flight, something like that.
Yeah, so these would be intra-city flights I don't think it needs to be quite 10 minutes. It can be of that order of tens of minutes.
Okay.
Not hours, right? I think that's
So just to clarify that we are not talking here about 150 miles or something like that. We're talking about moving inside a very well-defined urban environment.
Yeah. So the intent of that paper was to address the intra-city market, right?
Yeah.
Not intercity.
Or airport to city, for example, which is one of the applications
Exactly. Airport to city, for example, right? Like the canonical, one of the canonical use cases, right, is Manhattan to JFK airport, right? Or in LA, right? Somewhere from downtown LA to one of the LA airports. Or I think in, Melbourne is the other city being considered, right? So from, downtown Melbourne to the Melbourne airport, right? I think those are some exciting markets. I think ones that today are being addressed by helicopters or other kinds of vehicles. The beauty with urban air mobility and of course electric is that you get better operational economics such that it can become more ubiquitous. And the hope is that, with better noise profile, that you can now run many more of these kinds of flights than what you could do with helicopters today, right? So so the boundary here is those kinds of flights that would be in heavily congested urban environments where the difference in time is significant, right? So for traveling that same distance in the air, right, in 3 dimensions versus on the road, 2 dimensions is significant. Those are the ones that we will see really a penetration in those spaces.
Mm-hmm. Exciting times. What else are you working on at the moment? You had a very productive last year in terms of papers. Are you working on any other paper that we should be waiting for in the near future?
Yeah, we are actually. So the paper that we are, the work that we are involved with is, I talked a lot about chemistry, but now I'm going to talk about something very different, which is to estimate how much energy and power is left inside the battery. This is where it's very different from fuel. Fuel is very easy to decide how much energy is there. You just weigh how much fuel you have, right? Super easy. Unfortunately, with the battery, it's a closed system, which means that the only thing you can do is you can observe 3 things. You can observe the voltage, the current, and the temperature of the cell. And with that, you have to guess how it feels, right?
You don't see the electrons.
You don't see the electrons, right? So by observing, you have to sort of guess, whether it's in a comfortable shape, whether it's happy to do the landing mission, and so on. And so this is a project that was started with the Airbus A3 Vahana team, where what we have built is a very fast and accurate way to estimate whether your battery pack is going to be capable of doing the landing mission, right? And of course, landing and doing the aborted landing reserve mission in case you need to do that. And the key there is to be able to understand how the battery ages, and we call this the battery avionics system, right? So the core vision here is that we put the battery system in the same level playing field as every other avionics system that you have today, such that for a pilot, we give them all of the sort of instructive information about the state of the battery, that here's the amount of energy left, here's the amount of power left, here's the kind of landing mission it can do. And the most important thing is to be able to do that as the battery ages, right? This is the main challenging thing, because as the battery ages, then this becomes more challenging, because as an older battery cannot deliver the same amount of power, and we actually don't know when it cannot deliver the same amount of power, right? So these are sort of the main aspects to think about.
But what about, for example, in the iPhone? When I got the iPhone, there's a function that tells you what's like the battery health, and that's telling you some data about your battery. I mean, is it not that accurate then, or it's just a rough estimate?
Accurate. It is accurate, but aviation is different in the following way, especially urban air mobility, which is the context in which we're looking at this. Is the state of health monitoring is very easy for energy, just like it's easy to see the tank.
Okay.
Right, and say how much energy is left. It's easy to guess the energy. The difficulty is power. How quickly can I take out?
Okay, to put it in context.
To put it in context, right? To put it in the aviation context, right?
And the uses you want to do.
Yeah, exactly. And the aviation use is actually very, very tricky, right? So like you can't go to your iPhone and ask the question, At 20%, can I run YouTube and okay, can I parallel process YouTube and then do email and then do and then play something else, right? So that's the kind of load we are putting for an eVTOL, which is, I think, from a battery physics standpoint, right? It's really exciting for us because it's stressing the battery in a way that causes all kinds of failure modes. So we have to understand all of that, right? And where, and I think that the title of our paper sets the context here, right? Which is that for every challenge there is an opportunity, right? And we love challenges, right? So eVTOL in that sense is an amazing challenge for the battery designer, both from a cell engineer's perspective, but also from someone that tries to diagnose the energy and the power content of the battery.
Yeah, indeed. Well, I think we covered lots of ground, and I really appreciate your capacity to communicate all these very complex concepts in a way that I think everyone can easily understand. Because I have to admit, I'm not expert in this topic. As I admitted earlier, my chemistry notions from from high school are not very up to date. So it's been very it's been great for learning a bit better what are the challenges in this very promising field of battery technology. People that want to learn more about your work and follow the work you guys do, where should they go, and what type of resources would you direct them to? Of course, I would put links to the papers we were mentioning all the time, but where else could they go?
Yeah, so I think people can look up our group website, and I'll share the link to the group website to you. I am very active on Twitter, so people follow me at Venkvis, VENKVIS. Communication, as you said, right, is very important, and especially in these kinds of advanced technologies, the more we communicate to the public, that's how we can reduce the barrier to adoption. So that's why I spend an enormous amount of my time trying to help communicate these ideas around these kinds of new technologies and bringing down the fear level to the adoption of these new technologies. So please do follow me on Twitter. And
I do. I do already.
You do already.
But I recommend everyone else to do it as well.
Yeah, definitely. And I think I'll close with this parting remark, right? I think the exciting thing for the future of aviation is interdisciplinary, right? And I think this has been part of aviation for decades, and actually probably the full first century of aviation has been interdisciplinary. So in the article, we close by this comment that the way the next second century of aviation can progress rapidly is for the two communities to come together, right? The aerospace community and the electrochemical sciences community, right? That thinks a lot about energy storage and energy conversion devices. The fusion of those two is really, I think, where magic happens. And I hope that, through this, your listeners get excited to think a little bit more about batteries. And I think the future is extraordinarily bright. And I'm really excited for the second century of aviation.
I think that's an excellent concluding remark. We can leave it here for now, but I'm sure there are going to be a lot more novelties coming from the battery field. So more than welcome to come in the future and discuss it again and learn what's behind the scenes of all this progress we are seeing in the field of battery technology. Well, thank you very much, Venkat. And
thank you so much.
Looking forward to reading the new papers when they come out. So speak soon. Thank you.
All right. Bye-bye.
Before you go, and if you like this podcast, a quick reminder that it would be absolutely great if you could please give it a rating on Apple, Spotify, or whichever platform you're using, or recommend it to a friend or whomever might be interested. Thank you very much, and see you soon.